Okay, so last time we were talking about binary trees. So we kind of started making this differentiation between our linear linked data structures, um, like linked lists, stacks and queues, to our nonlinear linked data structures where we maybe have more than one child. So we started looking at binary trees specifically at the end last time, but we also talked about self-balancing trees like ABL trees and red-black trees, and then n-ary trees. Sometimes these guys are called syntax trees. So some programming languages, well, if you were to describe a programming language, you might describe it using a syntax tree for like what's allowed. So like, for instance, an if statement would be a node. So you'd have a node called statements, and under that you'd have something called an if. And an if would have a syntax tree of if opening curly brace, well, if opening parenthesis would be a separate node, Boolean expression would be a separate node, closing parenthesis would be a separate node, and then that whole thing would be followed by a statement. For instance, usually it's a block statement, opening curly brace, closing curly brace. So since different lines of code have different numbers of tokens in them, so a while loop and an if statement have a certain number of tokens, where a variable declaration is just going to have the type, the variable name, the equal sign, the value. And the value is anything that's an expression, followed by a semicolon. So you can describe that in an n-ary tree format or a syntax tree format, where it's the number of children of a node tells you how many individual tokens there are inside of in that case, a specific statement, something like that. So it could be a way of representing languages. But we're focused on binary trees here at first. And we talked about kind of a truth here that a tree is a collection of subtrees. And I mentioned something here for Noah that it's going to lend itself to pseudo recursion, and we'll see that today. So for example, the rule for binary trees says that everything to the left of a tree, well, right now we're just looking at a generic tree here. So here's a tree that just has a bunch of numbers split out. This guy has 3 children. So this tree is relatively meaningless. It looks pretty, ish, let's say, but it doesn't really give us any sort of structure that we can do anything with. Remember, the idea of these data structures is for them to be tools that help us solve problems. So with that in mind, we talked about the different parts of the tree, the root of the tree, the leaves, and the children. But we talk about binary trees specifically. So binary trees, each node has at most two children. Everything to the left of a node is going to be less than or equal to that guy. Everything to the right of a node will be greater than that guy. So, and then we saw an example last time where we took the exact same values. These are the exact same values added to the tree in a different order, and we got 2 very different trees. We would call this guy definitely better than this guy from a balance perspective, even though technically this guy is out of balance because the left side is more than 1 off from the right side. But this guy is horribly unbalanced. But we're not going to worry too much about that from our world right now, but just understand this concept that the exact same values organized in a binary tree can produce different binary trees if they were added in different orders. And we're going to actually implement one today, and we'll see this. Okay, so questions about the concept of a binary tree right now?
I don't know if we went over this, but did we talk about like what pros and cons of non-linear linked lists and linear linked lists would be? Like what in like practical uses, what would set them apart?
Well, okay, so and this kind of goes back to what I said a few minutes ago, is try not to get too hung up on each of these guys as being like this de facto, like a linked list. A linked list is an idea. A stack is an implementation of a linked list that's even a more focused idea, right? So a stack is a very simplified linked list, but it's still an idea, first in or a last in, first out queue. But now you've seen some of the things that we've tried to solve with stacks. We did Towers of Hanoi, where we had to amend our idea of a stack to be a little bit more, where that stack played by the Towers of Hanoi rule. So we technically had a data structure called a Tower of Hanoi tower that operated much like a stack operates, but had some additional rules associated with it. So any of these data structures that we're talking about, we want to think about as kind of like almost a starting point for problem solving. So, you know, it's not worth like saying, well, which is better, a linked list or a queue? You know, there isn't a better. You know, one of them is a simplified version of the other one, but if that's all you need that tool to do, you know, when you go to Home Depot, you buy the exact tool you need, not a tool that can do 40 things, of which you only need one. You buy the tool that you need. So when we talk about linear versus nonlinear, again, one's not better or worse than another. It comes down to how are we going to represent things. If I took this exact same data here and I put this inside of a linear linked list, and I just had all these values, you know, just if I just had them linearly written out. So I had 2, 3, 5, 7. Here, we'll just write it here. I'm just going to randomly pick them. 3, 2, 5. Well, here, I'm going to go from the bottom up. So we'll say, just so I can make sure I don't miss any. 5, 3, 3, 2, 5, 7, 13, 90, 17, 111. So this is this exact same data represented linearly. All right. So now if I want to search through this data, I want to find the 19, let's say. There is no 19. I want to find the 17. All right. So how am I going to have, if I give you something that looks like this and I want to look for a 17 in there, how would you go about searching that? If you wrote a program that searched this guy for a 17, what would you do? You'd start at the beginning, right? Because first of all, is this guy sorted? This data is not sorted. We know what trivially sorted means. It means stuff's in a one list, but at the very least, I haven't given you any information that this is sorted. And at a glance, you look at this and you see, well, that's definitely not sorted. So in order for me to find a 17 in here, I'm going to just have to flip through this because this is like a deck of cards, right? I'm going to say, is this a 17? No. Is this a 17? No. Is this a 17? Is this a 17? Is this a 17? Is this a 17? All the way till I get to this guy. That was what? 1, 2, 3, 4, 5, 6, 7, 8, 9. I had to do 9 checks. I had to ask 9 questions before I found my 17 there. Does that make sense? Now, if I take that exact same data, now let's go this route. Could I sort this and then find the 17 more quickly? Well, I could. Let's put this in order. So what do we got? We have 2, 3, 3, and 5, 5, 7, 13, 17, 90, 111. All right, so now it's sorted. So now I want to find the 17. Does it help me? If I want to search for the 17 in this, did having it sorted help me at all?
Not by much.
Okay, well, depends how I choose to look at it, right? So we're actually going to see a truth here in a second, but you know, I would say, okay, well, I'm just going to, you know, 1, 2, 3, 4, 5, 6, 7, 8. I saved myself one thing by doing what's called a linear search. So in this case, I can do a linear search. Let's actually just put that on a slide. Searching data. Linear search checks each value sequentially. Takes what's called linear time to complete. Which means if I'm searching for an item n times, it's going to take on average n checks. Potentially, because it could be the last item I'm finding each time. So this is linear time searching. I just start at the very beginning and I hope for the best. I hope the number I'm searching for is early on. If it's not in there at all, I'm going to get all the way to the end, ask a whole bunch of questions and never find it. All right. Now, we also have something called a binary search. Now, I'm going to come back to this here in a second. Let's look at this here first. So we saw that looking for a 17 in a linear linked data structure, the way we have it set up, was not all that efficient. We can certainly look at this and say, well, you know, over time, I'm probably going to be able to come up with ways of making that faster, and maybe sorting it as the starting point for that, hint, hint. But what if I was looking for that 17 in my binary tree here? Well, I'd start at the top of the tree. I'd say, is this a 17? Well, the answer is no. So I've checked one thing now. Now, the question is if the 17 is found in here, will it be to the left or will it be to the right? Remember, everything to the left is less than or equal to
the right.
It'll be to the right. So that means I've cut out half of the data in a balance tree, right? So in this case, actually more than half of the data. Then I know my 17, if it's there, is not there. So I'm going to check this guy. Is that a 17? Nope. Will a 17 be to the left or to the right of that guy? If it's there, it'll be to the left. Is this a 17? I found it in 3 moves. Does that make sense? So you see that the average that you'll have by storing things in a binary tree format, by having it follow the rules of everything to the left is less than or equal to, everything to the right is greater than, I have by nature my data already sorted in a way. You're going to see what that means when we look at tree traversal here probably today. If not, we'll look at it on Thursday. But we have this idea that because I've stored the stuff in a very specific manner, searching for individual values in here is quite efficient. That kind of makes some sense? So we start thinking about the types of problems that could benefit from efficient searching of data. Well, databases would be one thing when I need to search through and find something very quickly. You know, purchase orders, records. Amazon has zillions and zillions and zillions of orders. When you need to look up all the orders for an individual person out of their zillions of people, that's something that's going to have to look through a lot of records. And finding that quickly rather than going through, you know, customer number 0, customer number 1, customer number 2, so on and so forth. And, you know, trying to find a needle in a haystack as opposed to being able to kind of ping pong your way down, and at least every single step you take, you're cutting the amount of things you're looking at in half. All right, and this guy is called a binary search. So binary search requires, and sometimes, I think officially it's not called this, but sometimes you'll see it referred to this as a dictionary search. So a dictionary search requires that the data be sorted. So when you pick up a dictionary, don't you start off by making the assumption that all the A's are in the front and all the Z's are in the back? The thing's already in order, right? It's alphabetical. If a dictionary was not in alphabetical order, would it be harder to use? Not that we use dictionaries anymore, we just Google it, but That's actually going to be a funny thing. How many of you have never used a dictionary? Is that a thing? Do people still use dictionaries at some point, or is it just something that pops up as a Google search result sometimes?
Back in the day.
back in the day. But you know, if you think about the tool, when somebody says it's a dictionary, that comes with connotations, right? You're like, okay, well, this has a whole bunch of words in whatever language the dictionary's in, and those words are in alphabetical order. So that if I'm looking for a word, if I'm looking for the word kick, right, I would obviously go to the H's where hands are, because that's what we kick with, right? That was for you, Noah, as well. All right, so if I'm looking for kick, I'd go to the K's. Now, you would kind of make a guess, right? You know, you kind of flip to ish, the middle-ish, you know, about where you think the K's are in the alphabet, and then you look at what word is in the middle of that page, i.e., you look at the top of the page, and then you say, well, is this the word I'm looking for? No. Should the word come before or after this? If it comes after, you rip the book in half and go to the center of the next portion of the book, so on and so forth. So you can keep cutting your data in half, assuming your data is balanced. So that's what a dictionary is. Now you can implement a binary search using a normal linear data structure. Where's mine? So I can take this guy here and say I'm looking for a 17. So I can split the data in half. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can go to bucket 5. And you can decide which is the winner here. Let's just start with the 5 here. So is this the number I'm searching for? No. Is the number I'm looking for 17? Is it before or after this? It's after this. So now I'll just look at this portion of the list. So I'll go to the middle of that guy. Actually, I think based on the way I did my first math, it's this. So I'll go to the middle of that guy. Is this the number I'm looking for? No. Is it to the left or to the right of this? It's to the right. So I'll go to the middle of that guy. Is that the guy I'm looking for? No. Is it to the left or to the right of that? It's to the left. Is this the guy I'm looking for? Yes. All right, so I was able to cut down my number of searches on average. Remember, sometimes with a linear search, if I'm searching for a 2, you're not going to get any more efficient than a linear search here. Found it. First place I looked, there was my 2. But if I'm searching for 111, or I'm searching for a value that's not in this list, I have to go through all the elements of that database, of that list. Okay, so nonlinear linked data structures still give us the benefits of memory efficiency, in that these guys do not have to be stored contiguously next to each other in memory. But because we've added another dimension of structure to these guys, the idea of ultimate dimension, not non-linear, means anything not in a line. So we could have, in this case, we have a 2-dimensional thing, but nothing keeps us from having a 3-dimensional cube-based data structure, which would be like the linked equivalent of a 3-dimensional array. So we have 2-dimensional arrays, which is a grid. A 3-dimensional array is a cube, X, Y, and Z, if you just want to think about it as 3-dimensional space. But those are, all these different things are what we might use as programmers to represent things from real life. Right? If I'm creating a program to represent a Rubik's Cube, well, since it's a cube, I might use a 3-dimensional array to keep track of the X, Y, and Z values. Now, since a Rubik's Cube doesn't have that many cubes, I might choose, and it's already a known entity, I might choose to use an array for that and just take up all that contiguous memory because I know exactly the nature of the beast, right? But if I'm dealing with a procedurally, think about it like a video game. Some of the newfangled things that some of the newer open world games say is it's a procedurally generated world, where we don't know how big the world is or where X, Y, and Z is going to be at any particular point, because when you first load the game, the world is generated for you. And if you play again in a week, you're playing in a different world. It's a similar looking world, but the map is different because it was procedurally generated. Well, with something like that, since you don't necessarily know where one thing is relative to another thing, having it stored in contiguous memory doesn't really benefit you, other than making you take up a whole lot of memory at once. Whereas if you could store only parts of the map in memory using a linked list or a non-linear linked data structure, you are more memory efficient while still being able to expand and contract as the world gets larger or smaller, for example. All right, so all of these things that we talk about, and this isn't just with the data structures, it's also the things we dealt with before this. It's no different than tools at Home Depot. You walk in the door, you need to solve a problem, you see if there's a tool that already exists that helps you solve that problem. If there's not, you might need to build something, and so to build something, you're going to need to get the components that you're going to need to put it together. In our case, if we need to build a linked data structure, we're going to need nodes and an idea, right? Nodes and edges, something to fasten them together. So the links between our nodes are like the screws to screw a couple of pieces of wood together, right? These are the things that actually connect two things to each other. All right, so I mean, a little bit of a long-winded answer, but hopefully that kind of puts this into some perspective of what we're dealing with. You're not memorizing binary trees. What you're doing is you're considering a primitive nonlinear linked data type, like a binary tree, and you're saying, well, in and of itself, this guy can be handy, but also things that I might build upon using this as the base could be beneficial for solving different problems, just like Towers of Hanoi, where we used a stack as the base for the tower and then just added a little bit of a twist to it. Does that make some sense? So,
I just have a quick question.
go ahead.
When they say procedurally generated or randomly generated,
Yep.
there's some truth to that, I think, right? Because they have to design what they want. Like, I know for some things, like this one game I used to play called Spelunky, it's kind of like where you go through dungeons and whatever, and they say it's randomly generated, but really there's a select number of ways they have the way it lays out, and based on which ones generate first, they have to generate the rest in a way. Like they already have designed it. They pick and choose each time you play. So I don't know, it just kind of reminded me of this just because it seems like...
Yeah, so it's probably something like this. You know, we have our puzzle pieces here for putting together this tree. And the order in which we connect them to each other will produce different trees, but there is still a finite number of trees that we can produce using this organization. And in a video game where maybe certain, I mean, in our world here, we have a lot of unique trees we can produce because there are no rules about which node can be attached to which other node. Where in a dungeon type thing, you know, you might have a certain thing that might not make sense. So for instance, your entryway to the dungeon probably shouldn't be a hole in the ground. You just start off the game falling or something like that. So there's going to be some additional rules about that procedurally generated thing where, you know, a certain kind of area cannot be directly attached to another kind of area because they're not compatible with each other. You know, certain Legos can't plug into other Legos because those Legos, they don't have a way of interjoining. Or, you know, you'll never be able to complete what you're trying to do. There has to be some semblance of order in there. So I think that's probably true with procedurally generated worlds as well. If, you know, all the water spots need to be congregated together, you can't have a little piece of a lake right in the middle of the desert. And then just so, you know, yeah, we put the lake puzzle piece here randomly because that's how we generated the world. I guess you could do that, but it would be weird, right? You're walking around the world and you just have basically puddles in different places and, you know, things like that. It just wouldn't feel real. So to your point, there would have to be rules associated with it. So you would have a more finite number of things that could be generated. But the larger the world gets, I'm thinking about a game like No Man's Sky, where they have billions of worlds. So each one of those worlds plays by that same rule, where similar terrain probably needs to be, randomly generated near terrain that looks similar, but they can just randomly generate duplicates of that world that have different versions of terrain and different monsters that are on there and all that jazz. But everything's going to be finite. There's only so many different ways you can put together that puzzle, even if there's no rules attached. So this tree, there's only so many permutations that I could build this tree. All right. So let's get into designing our binary tree. So binary tree is going to be a what? Now, I'm going to kind of remind us of something here. Where did I put it? Here. A binary or a tree data structure is a collection of subtrees. Okay? This guy is a collection of subtrees. Well, we're going to have a top of the tree. So a binary tree is going to have a root. And and then it's also going to have a left child, and it's going to have a right child. Now, a root, we're going to say, is a payload. That's going to be our value, the thing that lives there. The left child is a binary tree. The right child is a binary tree. A binary tree is a collection of subtrees. So the very top of it will be a binary tree that has no payload, no left child, no right child. That's an empty tree. And we can even say there is no such thing as an empty tree. An empty tree, the simplest tree we might have is the tree who has a root but doesn't have a left or a right child. That's the simplest tree. All right, so this is the data structure for a binary tree. Let's go over here. I already clicked that. And let me get this guy open. And we're going to start oh, did it just crash? Oh, maybe it was in the middle of being updated. I'm going to open a folder. Go into 300 here. I'm going to create a new folder, and we're going to call this guy binary tree. And that's the folder we're going to open. All right, and we'll go ahead and get ourselves a working program here real quick. So we'll have our driver.cpp include, and actually we've been using IOStream, right? IOStream using namespace sys. Int main not sys. What's the name of our main namespace?
I think it's STD.
Oh, standard, yeah. All right, so this should give us our hello world guy here. Oh, why is my shunting yard out there? Oh, I was testing somebody's program. It's somebody else's shunting yard. All right, so we'll say g++ star.cpp /a.out. And there's my hello world. So we have a working program now. All right, so now I'll go ahead, just so I don't forget. I'll do my git init. And then I'll copy. GitHub something. All right, so I have my GitHub push now in this directory. So we're going to go ahead and we're going to give ourselves a binary tree.hpp. Right, and this guy is going to be a class called binary tree. And we're going to have private members. And we're going to have in here, we're going to have a int payload. We're going to have a binary tree left child and a binary tree. And these are binary tree pointers. Just as a quick question, what's the difference between a binary tree and a binary tree pointer?
It's the difference between passing somebody a piece of paper that has the address of a house versus passing them the whole house.
Yep. So this is the house. This is the piece of paper with the address of the house. So we will pass a pointer to the left child. Then we'll have a public section here. We're going to need our constructor for binary tree. And this guy will take in a payload. All right, let's just start with this. Actually, we probably want to have a way of adding a node as well. So we'll have a void add payload. Actually, we'll just call it add. We're adding something to the tree. And this guy will take in a payload. And ultimately, he's going to find a home for that guy. All right, so that's our binary tree. So now let's go ahead and let's add our binary tree CPP. This guy will include binary tree HPP. We'll go ahead and give ourselves our functions. All right, so when we first build a binary tree, it's going to have a initial payload. So what will we do? We're going to set this payload equal to payload. We'll set this left child equal to 0, this right child equal to 0. This initializes a binary tree. So it's like we planted a seed. So there's our one node that's in our simplest tree, even though we don't have nodes here. Remember, a binary tree is a collection of subtrees. All right, so the simplest binary tree will be a single payload with a empty left and right child. When I add something to a binary tree, well, first thing I'm going to do, well, I know that I can't add it to myself, right? Because if I exist, that means that if I exist, that means I already have a payload, because the simplest binary tree is right here and its payload already is filled. All right, so I know when somebody's adding a payload here, I know I can't add it to myself, but I do need to find out if it should go to my left or it should go to my right. So I'm going to say if payload is less than or equal to my payload, it should go to my left. Should go to my left. Else should go to my right. All right, so if it should go to my left, then what do I need to do? Well, I have two options. The easiest solution is if I don't already have a left child. So if not this left child. If I don't have a left child, I now have a new left child. So this left child is equal to a new binary tree made out of this payload. That's what the left child will be equal to. So if I don't currently have a left child, I will plant a new tree to my left with that payload. Else, if I do already have a left child, what do I want to do?
You gotta see if it's less than or greater than the one you're currently looking at, or the left child.
Okay. How would I ask that question?
Can you recursively call the if statement you already have?
All right, we're pushing in the right direction here. So what do you mean recursively call the if statement I already have? You want to ask this question again?
No, the one above it, the one we're in, the payload less than or equal.
Okay, but who do you want to ask that for?
I guess for the else statement.
Well, when we ask it for this guy, we're saying, is the payload I'm trying to add less than or equal to my payload? If we're in this else here, you want to ask, is the payload I'm trying to add less than or equal to my left child's payload? Right?
Yeah.
You want to ask the same question, but you want to ask it for one of your children. Is that what you're getting at?
I think so.
All right, so this goes back to me saying last class about pseudo recursion. And this is where recursion becomes very powerful, or things that look like recursion. In this case, it's technically pseudo recursion. So let's walk through this one more time. I know I can't add it to myself. If I'm in add, I know I can't add it to myself because I wouldn't exist if I didn't already have a payload. So I need to find out, should it go to my left or should it go to my right? If you go to my left, that's what this says, then my easiest solution is if I don't already have a left child, I'll just create one. No harm, no foul. Easy. Otherwise, if I already have a left child, the question is what do we do? Let me ask you this question. What kind of animal is my left child? Is it a cat, a dog, or a binary tree?
Dog.
It's a dog, right? It was a trick question, but it is a dog. So it's a binary tree. How do we add values to binary trees?
With the add
With the
function.
add function. So this dot left child add payload. That's how we add the payload to our left. We tell the left child, who's a binary tree, to add the payload. Done. So do you see what I mean by pseudo recursion? We're writing the add method right here. I'm calling the add method within itself, but I'm actually not calling my own add method. Instead, I'm calling my left child's add method. Why? Because the add method knows how to add a payload to a binary tree. That's what he knows how to do. That's what I need to do right here. Right here, I said, I don't have a left child, so I'll go ahead and plant a tree to my left. That was easy. But if I do have a left child, what do? I ask him to add this payload. No longer my problem. I pass the buck. Does that make sense? Similarly, if we're going to the right, we'll ask the same question if not this right child. If we don't currently have a right child, then we'll go ahead and plant a tree. Otherwise, I already have a right child, so what will I do? I'll ask him to add this guy. That makes sense? That's what add does. So do you see how simple add is when we start thinking about it in the context of, we'll call this pseudo recursion, because it's technically calling somebody else's identical method. But what we're doing is we're starting to like spell out, if you think about a program, especially as programs get more and more complex, we want to think about them as kind of like a play that's going on stage. And we're the director, and we're giving directions on what should happen on stage, who should go where, what should do what. So in this case, we're saying I have several binary trees on stage, potentially. Okay, if I'm standing here all alone, meaning I don't have a left child, I need to hire an actor to play the role of my left child. And I'm going to give him this payload to take care of. Otherwise, if I already have a left child, I'm going to hand over the precious payload to him and say, deal with this. You know, get out of my face. It says something like that. All right, does that kind of make sense? All right, so that's add. Go into driver here. And let me steal my string of numbers here. So I'll go ahead and create a binary tree. I'm going to need to include binary tree HPP. So I'll create a binary tree pointer, call it the tree. And this guy's going to equal to a new binary tree. And I'll pass this guy the 5. Then I'll say the tree add 3. Three, 2, 5, 7, 13, 90, 17, 111. Three, 2, 5, 13, 90, 17, 111. All right. What will the output of this program be?
Memory address.
Memory address, good. So there's our memory address. And what is that memory address? That is the address of our top of our tree, the binary tree that lives at the top of our tree. Now, if I were to print out this guy's payload, I currently don't have a way of getting his payload because his payload is a private value. So what I'm going to do here is I'm going to say void display. See how we're doing on time. Okay, I'm going to show it to you the full way then. So we're going to say display in order, display pre-order, display post order. And I'm going to go ahead and add those in here so we don't forget. And then we'll explain what they mean. Okay. All right, and just real quick before I go and write that, let me also, just for the sake of completeness here, let me go ahead and give myself a get payload just so we can prove that this got put together the right way. So we'll say int get payload. That way binary trees can give us their payload. We also need them to actually, well, this is a good example not to use that. All right, we're just going to do the get the payload here for a second, then I'm going to connect the dots on something. So I'm going to say the tree get payload, and that's going to give me the 3. All right, so that's the, or I'm sorry, the 5. That's the top of the tree. Now, if I were to get his left child's payload, his left child, when we go to add the 3, we try to add a 3 to the 5. Should the 5 go to the left, or should the 5 go to the, or should 3 go to the left of the 5, or should 3 go to the right of the 5? It should go to the left of the 5. So I need to teach my binary tree binary tree pointer get left child, binary tree pointer get right child. And I'm going to add these to my binary tree for now, just to test it, but I'm actually going to take them out here in a few minutes. I'll explain why. Oh, I haven't written. I haven't written that yet. I add it to my header. So I'm going to write these guys here at the, actually that's still inside that. All right, I'm going to give you fair warning here, though. In a few minutes, I'm going to try to trick you. All right, so I'm going to go ahead and I'm going to say this guy will return this payload. Oh, I need to put the binary tree thing here. This guy will return this get left child. I'm sorry, get this left child. And this guy will return this right child. All right, so these are my getters. Now, remind me, why do I need getters and potentially setters? What's the purpose of these guys? Why do I need them in the first place?
To access private members.
Okay, to access the private members. Where are private members accessible?
Inside the class itself.
Okay, so when we, and I'm going to ask you to be more specific here in a second, but when we, so we have three different options, right? We have public, private, protected. All right, so, and actually there's a fourth, and I'll go ahead and put it in the context of C++. So when we talk about class security, Java had public, private, protected. And does anybody know by default, if you didn't choose public, private, or protected before a field or a method, what its security was? It's called package level security. So anything in the package that that program is in, which usually we're operating out of the default package unless we specify a package, falls into that. C++, we have public, we have private, we have protected, and then their equivalent of package is something called friend. And actually that would be old, an old version of it. Now it would be a namespace. Okay, so now the definition of all these things are the same. So we're going to focus in on the C++ side of things here because they are identical. So remind me again, what is the rule for private? Where are private, well, where are public members accessible? Accessible everywhere, right? Where are protected? Well, let's go with private. Where are private members accessible? Now you told me that it's in the class itself, right? I said I'm going to ask you to be more specific. So be more specific. You're not wrong. It's just very important that we are extremely precise with this, and I'll show you why in a minute. Any takers? So far what we have is accessible inside of this class. That's effectively what you've said at this point, right? So I'm going to modify this a little bit. We're going to say this is accessible inside of a class with the same name as this class. The reason why this is important is if I go back to my binary tree over here, these private members, payload, left child, right child, they are accessible anywhere inside of any instance of binary trees, which means that the left child, so here, for example, I can do, we'll just do it inside of binary tree, CPP rather. So for get payload, for no good reason, actually, I'll just cheat here. So we're going to say int get left payload. For no reason other than just to prove this thing. We're going to take it out here in a few minutes. All right, so get left payload. So for this guy, we can return this, and we're just going to assume that we have a left child payload. Notice I'm not calling his get payload. I'm directly accessing his payload field, his private payload field. So I'm currently in this instance of binary tree, and I'm talking to my left child, which is another instance of binary tree, but I'm directly accessing his private field called payload because I am currently in the class binary tree. And so binary trees can access each other's private members because we're in a class with the same name. And let's prove this real quick out here. So the tree get payload. And then we'll say the tree get left payload. Where get left payload should give me this 3, but the way it's giving it to me is through by saying get my left child and then directly access his payload. Does that make sense? I'm not calling his public function called get payload. I'm directly accessing his private member, which I'm allowed to do because I am in a class called binary tree. I'm accessing a different instance of binary trees private member, but I'm still inside the class called binary tree, so I have access. Kind of like keep it in the family type thing. So this should give me that 3. So there's the 5 and there's the 3. All right, that makes sense? It's an important nuance, and even though it might seem somewhat trivial, it's actually extremely important that we understand that concept because there is a differentiating factor between punchline here is depending on where I intend to access the payloads and the left and the right childs, the right children, I may not have to give myself getters because out here, if I choose not to directly get payloads and get left and right children, I won't need access to it out here. I'm in a class here called driver. Actually, I'm not even in a class, so it's even worse. So I would need to have public ability then. But I'm definitely not in a class called binary tree. So I'm saying that we can get rid of get payload, or at the very least, we can get rid of left, right child, and get left payload. We might be interested in getting the value that lives at a particular node in our binary tree. But even then, even get payload might not be handy out there. In fact, I'm gonna tie our hands behind our back a little bit. It should not impact you, but I'm sure it will impact you. Hint, hint. Okay, so I'm gonna force you to wrap your mind around this, this concept we just talked about. Okay, but I have given ourselves 3 different functions here: display in order, display pre-order, display post-order. And we're gonna talk about what those guys are here in a second after I extract our couple of functions: get left, get payload, get left, get right. Okay. Those guys. And in driver, get rid of those because no longer do I actually have my those functions. So right now my output will be nothing. Okay. So now let's go talk about what in order, post order, pre-order is. This is called traversing a tree. We have 3 methods. 3, yeah, methods is fine. We have something called in order. We have something called pre-order, and we have something called post order. Notice those should line up with our function calls: in order, pre-order, post order, that I'm going to be asking you to write for Thursday. These all, with the order in which we visit the parts of the tree. In order says visit left child, then ourselves, then right child. Pre-order says visit ourselves, then left, then right. Post order says visit left, visit right, visit ourselves. Okay, so I'm going to go ahead and give myself this guy as my example here. Oh, let me just steal this slide. So we're going to say, what did I say first? Pre-order. Post order. And in order. Okay, so in order says we're going to visit our left child, then we're going to visit ourself, then we're going to visit our right child. So if I were to visit this entire tree in order said if I start here, I'm going to visit my left child. So now this guy gets put on hold. Red flags, recursion, recursion, recursion. So this guy gets put on hold. Now I'm on this tree. I'm visiting this guy in order. What do? I visit my left child. Now I'm at this guy. We visit this guy in order. What does he do? He visits his left child. He has no left child. So now we bounce back up. In order, the second thing we do for in order is we visit ourselves. So I'm going to visit the 2. Then we visit our right child. Now, this is a new binary tree. We're visiting this binary tree in order. So he visits his left child first, which is a new binary tree. He's going to visit his left child, not existent. Then we're going to visit himself. Then he's going to visit his right child, non-existent. And we bounce back up. He's going to visit himself. Then he's going to visit his right child, which is a binary tree. We're going to visit the left child, not existent, visit myself. And I'm going to visit my right child. Bounce back up, bounce back up, bounce back up. Now we're going to visit ourself. Then I'm going to visit my right child. He's going to try to visit his left. Then he's going to visit himself. Then he's going to visit his right child, non-existent. Bounce back up, visit myself. Now we're going to visit our right child. He's a binary tree, so he's going to visit his left child. He's a binary tree. He's going to try to visit his left child, non-existent. He's going to visit himself. And he's going to try to visit his right child, non-existent. He's going to bounce back up. This tree is going to visit himself. Then he's going to visit his left child. This is a binary tree. He's going to attempt to visit his left child, non-existent. He's going to visit himself. He's going to attempt to visit his right child, non-existent. Bounce back up, we're done. And what were we left with? Traversing that tree in order. We were left with our numbers sorted. Pre-order says we visit ourself first, and then we visit our left, and then we visit our right. So for pre-order, we're gonna visit 13, then we're gonna visit our left. This guy's gonna visit himself, then he's gonna visit his left. He's gonna visit himself, then he's gonna visit his left. Nothing there. Then we're gonna visit our right. He's gonna visit himself. Then he's gonna visit his left. He's gonna visit himself. And he's going to try to visit his left. He's going to try to visit his right. He's going to bounce back up. He's going to try to visit his right. He's going to visit himself. And he's going to visit his left. And he's going to visit his right. Then we're going to bounce back up, visit our right. Bounce back up, visit my right. Why do I keep forgetting to hit space? Visit my left, visit himself. Visit his left, visit his right, bounce back up, visit his right, visit himself. Visit his left, visit his right, bounce back up, bounce back up. There's our traverse order for pre-order. And we're not going to talk about why that might be handy yet. We will. Finally, post order. We visit ourself last. So post order for these will be visit all the way to the left. So we'll visit 3, then 5, then ourself, then ourself, then a 7, then ourself, then a 17, then a 111, then ourself, then ourself. All right, your homework for Thursday is to implement the display in order, display pre-order, display post-order methods. And you cannot have getters. without using getters for payload, left child, and right child, implement display in order, display pre-order, display post order. So if you had this exact tree built, like this exact tree, you would get these outputs from it. Questions, what I'm asking you to do? As you're doing this, remember pseudo recursion, and remember that if you're inside of a class called binary tree, you have access to the private fields of binary trees. Not just your private fields, but also your left and right child's private fields. All right, questions, comments, concerns, bribes. And it looks like from a while ago, Josh had a question. Why didn't you blurt something out? Is your mic not working?
Sorry, yeah. Would it be helpful to write a binary tree with the child in terms of like each child is a node, or would that complicate things?
I think that personally that complicates things. I mean, you could write it that way, but why write it that way if we have the truth that a binary tree is a tree of trees? This guy's a binary tree. This guy's a binary tree. This guy's a binary tree. This guy's a binary tree, so on and so forth. As programmers, we're meant to represent, we should be trying to represent things as true to life as possible. A binary tree is a collection of binary trees linked together. You can call this guy a node if you want, but he's still a binary tree. So why give him a new name if he's still the same thing?
That makes a lot of sense. Thank you.
Other questions?
I have a question. With visiting, it seems like sometimes when you said visit, you added it to the line, and sometimes you didn't, like if you visited yourself again. What are the terms for when you...
Well, visit, when I'm saying visit is you're going there, but it depends on if you're in order. If you're in order, you will add it to the list. If I'm visiting this node right here, but I'm visiting it in order, I'm not allowed to announce myself yet. I have to announce my left first. And only once that returns can I announce myself, because in order says left, then myself, then right. Pre-order says when I visit this node, for example, I immediately can announce myself. I can add it to the list because in order says myself, then my left, then my right. Post order says my left, then my right, then myself. So I'll talk about myself at the very last moment if I'm visiting in post order. So that's why these guys have different orders. I'm visiting the same tree, but the way I'm visiting those nodes and announcing, so if we think about each node announcing itself, the order in which they can announce themselves, if we're telling them to call out their name, call out their payload, the order in which they're calling it out is different depending on which of these rules they're following. Does that make sense?
Yeah, that helps. Thank you.
All right, and if you noticed on Slack, I also posted up the dates for the senior seminar presentations. Strongly encourage you to attend those on Zoom. So save the date. It's Tuesday and Wednesday the week before finals. Go to as many of them as you can. Support the seniors. So that's the scoop. So put that on your calendar if you wouldn't mind. And otherwise, I'll see everybody on Thursday.